this Thursday. So today is last week we have seen the available resources for the critical minerals, and also we've seen the what are the geopolitical role playing those critical minerals for the other countries, especially for China, and what are the available things in those other countries. Now we will see the advancements of mineral processing, and we are also looking at the existing technologies and what advancements have to be done for the process of the critical minerals. For that, I would like to invite Professor Narasimha Mangareddy from IIT Hyderabad.
Yeah, thank you, Swarika. I guess Professor Mohan suggested that better I'll start today because Professor Mohan was teaching for the last 2 days, and I'll start first session, and then maybe after tea break, probably Professor Mohan. Okay, is it coming? Is it moving? Okay. It's okay. I think for you, you are getting the voice, right? Yeah, fine. Okay. So today's lecture, I focus mostly on advances in mineral processing, which is very important for when you deal about a primary and as well as a secondary sources. And to the extent even tertiary also, for example, recycling of the electronic waste and metal scraps, still you need some kind of a preconditioning. When I say preconditioning, they are about, for example, if you take a PCB boards, you cannot straight away use for leaching or extraction. So you have to now eliminate many of the other components, for example, plastic, or even if you have a silicon and other things that are basically you needed in the different matrix level to be eliminated. So for that, I think what we do is we try and do a lot of shredding, right? When you do the shredding, it's actually you are trying to reduce the given material into small pieces, and to the level where we see that there is a maximum liberation of whatever you are interested from other matrix, and that is what we refer as the size reduction or a combination. So, and with that route, from primary anyway, we need the mineral processing, and from secondary also you need some extent of liberation, and for tertiary also you need these unit operations to be done in a meticulous way. So when I look at that angle, so this is where the today's lecture mainly focusing on mineralogy as well as the the comminution, because both are interlinked. Without a comminution or a progressive size reduction, you may not be able to see what is happening with respect to mineral liberations. So that is what we want to focus on today. And then this is where the importance of critical minerals, I think Professor Mohan might have already mentioned a lot of insight on that and how they are important. So we know that they are very backbone for our modern technology, and also green energy enabler when you want to reduce the pollution or even the greenhouse gases. So this is one way of utilizing the greener solutions through the critical mineral, and also strategic resources. When you say strategic, again, they are very important for certain geographical advantage of the operations and economic growth, and also they exhibit certain unique properties. For example, we know magnets, semiconductors, and advanced alloys comes from these critical metals and minerals. So basically, we need it. And finally, the economic opportunity, because without this, if you look at it, you cannot sustain the economic growth. And particularly with respect to our domestic mining, processing and recycling, creating the jobs, innovation and resilience, these are essential integral part of all these processes that we target for economic growth. So in a simple sentence, if we try and place it, your supply security is equal to your national security plus economic competitiveness. So if you have these two, then you can able to meet your required supply security for any nation to grow. So in that context, we know the importance of the critical minerals. And again, this is again by one of our scientific advisor or Niti Aayog member, Dr. V.K. Saraswat. He made this slide particularly saying that this is what we focus on. So it is required for high-tech products and green technologies and defense. That is inevitable for all the critical metals, tend to lack substitutes and recycling processes currently in India. And third is, we also need to actually target for high concentration of extraction and processing. Current technologies, if we try and look at it, they are kind of moderate concentration levels. But I think for targeting critical minerals, actually you need to go for high purity. Without that, there is no value addition that we are making. And of course, what is important is because certain elements which we don't have, and then we have to have a seamless import resilience that we need to get into. And then the governance regimes, I mean, all that we are talking about, your environmental, again, sustainability issue also should be focused when you attempt these processes. So, and that is where we talk about what is the need for mineral processing for critical minerals. So, the significant concentration of the critical metals, I think, where is the pointer? Is this middle one? I think it doesn't come on the screen, right? Achha. Oh, okay.
Normal pointer there, like it.
Yes, yes. Yeah, so, okay, I think it is slow. Right, okay, okay, fine. So when you look at it, the significant concentration of critical minerals have reported in the mining and processing waste over the time. That means now, if you want to reuse this material for extraction of your critical metals, for example, coal fly ash is one of the now waste product that comes out of your particularly power plant. Now, out of that, there's a lot of valuable in terms of the rare earths. Now, this is basically being considered as a waste, but of course, 30 to 35% is being targeted to reuse in the cement industries. But still, you have 70-75%, which you need to still adopt for recovery of further. And environmentally, this fly ash is problematic. And second, if you extract further, then you need to target to do a further refinement of these materials, which are very fine in the nature. So an opportunity exists to meet critical metal demands through reprocessing of these waste. So that's where we look at it, need for critical mineral processing for critical minerals. Mining and processing waste have a significant different properties from the runoff mine. So though mineral processing is established very well for runoff mines for any processing plant, but there is a similar behavior that you can able to draw attention, but for the refinement. But they are not same as you treat for the runoff mines for the critical mineral waste and mineral mining waste. So this means that while overall mineral processing sequence for mining and processing waste is the same as runoff mine, but the best technologies to achieve the liberation, separation and concentration of critical minerals is very different. So the level of refinement that we target for utilizing the same unit operations should be different. And there are range of innovative technologies that are being used for liberate and separate critical metals from mining and processing of waste. So this, I think, these overall disciplines that we talk about, mineralogy, chemistry, and engineering, well articulated. I think you can see yourself where you are fitting. So for us, particularly when you talk about mineral processing, we actually are in the regime of between the mineralogy as well as the engineering stream, and then some overlap with the chemical as well as the chemistry is associated. But when you talk about specific to critical minerals, where we go with the high purity that we want to go. So basically the central regime, which is pyro, hydro and electro processes are inevitable for it. But then to go to that level, then you need to actually pre-process them or preconditioning such a way that you reject most of the gang in the beginning itself. For example, in the coal fly ash, if the rare earths are being found, let's say about 400 ppm, now that means you have to reject more than 98% of the gang in an overall sense to recover. But when I go for 94-98% of the gang rejection, probably if you directly attempt through the pyro and hydro and electro processes, then you need a lot of energy. Then why do we need to go and utilize the entire mass for subjecting for these processes? Can we do some free concentration using physical method? So that's where we come minerals engineering or mineral processing. So then if we reject, let's say, even 50% of the gang in the beginning itself, you are actually saving a lot of energy in terms of your leaching solvents that you adopt, or hydro and pyro metallurgical routes where they are very energy intensive. So that's the role where we talk about the mineral processing would come in a heavy way. And so specific to mineral processing, where we talk about two levels, beneficiation by physical methods and extractive metallurgy, where we go with the chemical route. And after that, I think we get your metal. And this process is very common for run-of-mine process materials, as well as even the critical minerals that you talk about it. But the refinement levels are different, concentration levels are different. Okay, so that's where the beneficiation is nothing but mineral dressing, overlap of physical and chemical methods depending on the product, where extractive metallurgy leaves off, metal processing begins for it to go on. So in that way, so now can we look at what are these mineral processing units? I think most of us are aware what they are there, but I'm just trying to place this as a recap of what we are trying to do in the mineral processing. Mineral processing, we do comminution. When I say comminution, crushing and grinding to the level of required targets. So crushing can be of multiple stages, starting from primary, secondary, tertiary, and grinding also can be again multiple levels. In fact, 4 levels also possible. Primary grinding, secondary grinding, tertiary, and regrinding based on your further gang matrix that you want to liberate your valuables. So all that are embedded in the crushing and milling. And once you reduce your target size where the liberation of the valuables are happening, then we need to also classify the particle, because some of the particle may not be broken to the required sizes. So you need to recycle back utilizing the classification devices. Once you have the classification devices embedded with the comminution circuits, then we know we are going to get our required product size range. But then how do you separate? That is where we go on different separation techniques, which I'll be dealing about the other next talk, probably next tomorrow, second or third talk, that I'll be focusing on separation of these by various methods, including flotation, gravity separations, and so on. So once we finish physical concentration as much as possible, let's say 30 to 35% in general for critical metals or minerals, then we go on further metal extraction and metal recovery through hydro-pyro metallurgical route. And so this is where we see, and again there you get a waste. So this waste, you can see everywhere it is getting accumulated, not only with respect to mineral processing, for every stage you are getting waste. And in fact, this waste is pretty important. And today we see we may not be able to really utilize it. But when you go back and look 50 years before, the coal flash that we generated long back is now a new source for us to look at it differently. And also same as if you look at one of the major city that you might have come across is Johannesburg. And if you try and fly in Johannesburg, you see big piles of mountains that you naturally see around the city. They are nothing but Johannesburg city actually established is a mining city, like Dunbar, where these mountains of piles that happen are nothing but a gold rejects. And today they are again reprocessing these waste. And not only for gold, but also other complexes of precious metals that they have it, and silver, and also other critical metals. So essentially, now every waste is now a new source for us, and today as well as tomorrow. And that is where we don't throw them away, but though some of them we can utilize it as actually. So we had a coal board meeting last week, and then there was one proposal saying that NML, I think National Metallurgical Laboratory, saying that we will extract the rare earths from coal rejects. That's a big surprise. And when we look at the data, they're still processing the data to collocate in some manner. But otherwise, their claim is rare earths in the coal washer rejects, which are, you see, are 300 to 500 ppm. This is significant. And we are trying to validate whether this is true or not with various samples. But otherwise, if that happens, now tomorrow around the Jharkhand, Dhanbad, or even Durgapur area, whatever the coal rejects piles are there, which are in the form of mountains, we can actually use them as a next level of feedstock for us. So that is where we focus on moving further. So now this essentially suggests that when you try and do this, comminution needs to assess the liberation levels. So I think my initial talk is mainly focused on liberation. I think liberation part, probably you can find these slides. Anyway, we'll also try and find out most of the material to be circulated as a PDF files for you after talking to Professor Mohan. And otherwise, so these are quite available for you. So what is this mineralogy all about? Mineralogy is nothing but a study of a chemistry, atomic structure and physical properties and the genesis of minerals that happens. I think if you are a geologist, you know what I'm all talking. But otherwise, for being chemical, civil engineers and mining engineers, they know what is this mineralogy is all about. We are looking at those kind of structures of these solid particle, how they form, and then the chemical bonding that they will have it with the other source of composites. So now, if you look at this mineralogy, there are many subfields. I think from geological prospect, if you look at it, there is again a descriptive mineralogy we talk about, where documenting physical and optical properties, obviously we see. And crystal chemistry, again, relationship, chemical composition of atomic structure. You need to relate to this every material about. Crystallography, again, how these, the relation between crystal symmetry and form of the atomic structure that they are there. And mineral genesis, where interpreting the geological setting in which the mineral forms from physical, chemical and structural attributes and its associated mineral. So for that matter, when you try and look at it, any material that is available or mineral, and one geological location to another geological location, the formation is, though they are similar nature, but the composition is very different. And the way you find coal in lignite Neyveli, South India, to coal that you find in Assam, very different in terms of the way they form and the structure and compositions. And we, based on that composition, if we analyze them correctly, then we'll have a better know how to deal and reduce this gang from further size reduction methods. So and further, there are other important terminologies that you need to also understand. Petrology, that is the study of origin of, petrology is the study of origin of the rocks in a largely determined by evaluating structure and texture and chemistry of the minerals by containing. For example, this terminology we use for coal. So then we say the coal petrography instead of the coal mineralogy. Okay. And geochemistry, which is again a chemistry of earth metal, which reflects the collective chemistry of the minerals they contain. And I think the geochemistry and petrology, they are related in a similar manner, but referring to different nature of the material that we talk about. And structural geology and tectonics, again, we talk about how, based on how they form the rocks and also how they orient with respect to your geological structure that is associated with the different minerals. And again, environmental geology, hydrology, certain minerals, they are very prone for your transport of the soil and again water and other things. So then based on those, you need to see biosphere and hydrosphere and atmospheric interaction basis, these rocks would get migrated. I think there is a lot of proven concepts on how gold particle will migrate. So majority of them, if you look at it, they are actually found near river basins area. And the reason is because they are actually much prone with respect to the hydrosphere that is associated with them, the natural transport that happens along with the soil that is consist. So essentially, these are the understanding of these, the minerals that you can talk about various concepts basis. And economy geology, which is we talk about what is the benefit that we can able to do mining and then subsequent processing. Then we talk about a cutoff grade and other things that is decided based on the economic geological aspects. So in a way, a mineral that now, if you look at from atomic structure point of view to the valuable metals that are associated, we can define them as actually is a naturally occurring solid with highly ordered atomic arrangement and definite chemical composition. Because they have this chemical composition that are useful for us to understand and extract it, and we are taking them whether the mineral is being defined based on this economic value that is coming out of that for a reference of ore or not. And usually it is formed in organic processes. But then there is always a question saying that is a coal is a mineral or fuel. So we say it's fuel, but it still contains inorganic substances which are ash contents. And they are also useful because when you look at your further refinement of the fly ash or a bottom ash to useful materials such as cyanospheres or the rare earths, they are still there, but in the traces amounts. So this is where we see from rock, which is mined, and then if you look at the minerals that are associated with the same rock, or the multiple minerals can associate with the same rock. Again, if we go into structure, elements point of view. So you see that how they are in terms of the quartz, how silicon is being associated, and even biotite is potassium, manganese, the magnesium and iron, aluminum, and also you have alkali feldspar which you use for other kind of elements. So we know we mine the rock, but at the end we actually target the metals. And that's how the value addition we target to go and refine it based on their chemical value that we know and structures that we know. So just to understand the involvement of current modern technology, for example, if you take a smartphone, how many of these elements we need it? You see plenty of them. And starting from screen, you need indium, tin, zinc, aluminum, silicon, and potassium. And also you need a lot of rare earths, which are also there. And battery, if you go, lithium, cobalt, copper, and aluminum. And again, if you go on the casing, other thing, of course, mostly they are magnesium, nickel, and boron, and carbon. And if you go on electronics, I think starting from quartz or silica, you have many of these critical elements that are being used. So essentially, when you talk about any smartphone, small gadget that we have in with us today, needs a lot of these critical elements to manufacture. And again, as we all know, that 95% of these critical minerals are being owned by China. That's why they are going to be dominant on the electronic field very soon. In fact, the production are heavily patented from US side, but I think very soon they are going to take over by China. So then this is again, we know we are very fancy about iPhone and all that. Even you need about 46 elements just to build one iPhone. And see what are those critical elements that we talk about it, starting from tungsten, nickel, and cobalt, indium, and you have about a gallium, and then we have a palladium and tantalum, all of them. So in a way, this is quite eye-opening for us to understand how critical minerals are actually playing a major role in the modern technology side, and especially in electronic field, and also energy sector, as well as other applications that I think Professor Mohan is being illustrating all the time. Now, going back to mineralogy, so when did it actually started? So it actually dates back to human civilization, and that is where we talk about mineral science begins with the age of reason, where 1556 is being reported formally that minerals are being identified, certain nature. And 1700s, measurement of the crystal geometry and symmetry, they started understanding the structure of these materials. And early 1800s, precise measurement of crystal symmetry, heralds of field of crystallography, analytical chemistry leads to chemical classification of the minerals. Again, it's very early 1800s. Late 1800s, creation of polarization microscope opens field of petrography and study of optical properties of minerals. Now you see, date back to almost 3 centuries nearly, or even if we talk about today, not nearly, we are in the 5th century of what is happening with respect to minerals and crystallography of it. Now moving further, so in the latest, the 1900s, X-ray diffraction measurements allow for precise measurement for internal symmetry and structure of minerals. And 1960, development of electron microscope allows for accurate in situ analysis of a mineral chemistry. And 1970s, we have again a TEM that started. And the 1980s, ion microscope allows for the study of isotope composition and mineral. And further, if we look at it, I think if I go back, I think we have now almost 2000 onwards, we have an atom probe. We could be able to see now electron level of the atom level of information. In fact, IIT Hyderabad has one atom probe where Professor Murthy, our director himself, is a expertise on that. And recently the SATI, which is supported by DST, is being utilized for procuring it. I think the equipment cost is about 9 or 30 crores just for one major piece. And in India, we have 3 of them, one in IIT Madras, where Professor Murthy himself established one atom probe. Third one is here, and second in IISc. So that's how the atomic level of these materials that you can able to see clearly using these developments of the microscopes. So moving on to mineralogy, which is our critical, focus today, is actually determines the recoverability of valuable mineral. And again, they are again interlocked with a given matrix. So if you look at it here, a rock that is there, which will have a different composition when you try and reduce your sizes. So not necessarily that every rock will have a similar composition of the valuable mineral. So then you get a different product for the combination, and then we try and see. And based on the level of size reduction that you go, you need to assess at every stage of a sequel size reduction that what is this, the liberation values or enrichment of the grade is happening with respect to these for the given rocks. So, and these are the mineralogy impact that we can able to see. Starting from, I think when I go with it, we mine rocks, but we concentrate on minerals at the end. So again, you see, your mining doesn't start with the target of minerals. Though you have overall geological area that you mapped, but you don't know where these individual minerals are integrated with the rocks. So that is where we go on it. So then you need to, so initial feasibility anyway we have to do. This is called any mining that you do, you need to get a bore well samples for different levels, axial and deeper levels, and assess what is the composition that is there. And based on that, mine planning will be made, and then you get a mine blast that would taken place, and then you get a progeny that is being blasted because of the mine activity. But once you get it, now what we need to do is we need to see after mining how much of this liberation is happening. Again, you need to reanalyze what is an assessment of these mineral on the surface as well as a volume wise. Then the second part that we go on is gangue minerals. Then gangue minerals are also important. So we cannot discard the gangue minerals because unless until we know how valuable mineral and gangue both are associated, we can think about the designing of your comminution equipment as well as the separation equipment. Then moving on to further, when you further subject for the various grinding level, and also you recycle back unwanted or unliberated metal back into comminution, then you also need to assess after comminution and classification how the value of these minerals are getting changed from the initial rock. So every stage, if you look at it, you have to actually have a process mineralogy that you need to be checked. And if you look at that way, in India, we actually are not practicing this for every mining sector. Probably the majority of them are very well thoroughly checked is the lead zinc, which is chalcopyrite complex mineralogy that you need to understand anyway to go for it. And I think the Vedanta group, Hindustan Zinc Limited, they are doing that at least to some extent. But then remaining minerals that we, for example, iron ore, as of now, we are blessed to have a high grade iron ore in India. And because of that, we are not too much worried about how these iron minerals are being associated with the other gangue minerals in the beginning. But when you go for finer size, for example, now today there's plenty of slimes being accumulated. Now, when you want to reprocess them or reutilize them, you need to understand further these mineralogical aspects. So that is where, otherwise, in theoretical framework, process mineralogy is needed at every stage of operation, starting from your crushing, grinding, recycling, the reclassification, separation, and enrichment through flotation and down the line till you get your mineral product that is ready for hydro and pyrometallurgical routes. So that is how we need it. So then this puts it in a different way, where that mineralogy is nothing but mineral liberation analysis, very important subject for applied for mineralogy and metallurgical processes also. Mineral liberation data are fundamental parameters used for processing plant design and optimization. And there are several systems developed again in the past for mineral liberation analysis. Mathematical models are there, but I think they are subject to for statistical data and then data analytics based model prediction. So right now we are not going into that direction, but otherwise today you can imagine that a lot of this geometallurgical data is being used for predicting the mineral processing plant performance prior before you start the plants. So that is happening because thanks for AI and ML, where they are able to do this now for a lot of data that is accumulated over the years. However, industrial applications of liberation data have been previously limited because of acquisition of mineral liberation data has been difficult and expensive to determine. But I think currently there are major developments are there already, and particularly electronics and also the computing technology, allowed them for accurate estimates of these things using fast and user-friendly liberation analyzers. So very popular. I think up to, I would say 10 years back, these three were very dominant. The SCM anyway is there, edocs basis. You can do it, but there is certain limitation in terms of the databases that are equipped. I think now, as on today, many vendors have come forward to actually extend the SCM edocs application for minerals also. Okay, and whereas the MLA is again established in Australia, Mineral Liberation Analyzer, and it's being widely used in Asia Pacific mostly. And TwinScam, again, it's established from the Australian, basically Asia Pacific as well as North and South Americans. They attempted this heavily. Now, out of these, I think I have a comprehensive slide which you can see. These are the various models as on today we have it. TwinScam, I think that is now with the Thermo Fishers, and MLI is also with the Thermo Fishers. And Mineralogica, this is with the GSIS, and Inca Mineral, this is Oxford Instrument. TIMA, I think TESCON, this is where TESCAN, this is with the TESCAN. And Bruker also, they have come up, AMICS, and RodScan, QuemScan, Light, and MinScan. So I think all these versions are basically what they claim is some of them that they have a huge database. So yesterday I was talking to Thermo Fishers, where they claim that they have 4,200 mineral databases that they have inbuilt with the extended FESCM with the automated mineralogy software. So obviously every vendor would try and attract you to use it, but otherwise as a user you should know where is your maximum usage of this instrument and databases that are available. Okay. Now, how it look like? So this is a MLA where I myself witnessed when I was doing PhD at JKMRC. So they developed the MLA, and it has actually, compared to SCM, you need an extra detector for getting additional images in the volumetric notion. And then once you know, let's for example, you have taken one sample, and then in that sample you try and identify what are the mineral phases that are there with the system, and then you map them in terms of the volumetric information wise, how much of each progeny that is there, and how it actually comes with respect to different mineralogical aspects. So you can do size wise, and also within the given size solid particle, it can detect what are the compositions of mineral phases are there. We are talking about mineral phases, not elemental. And anyway, elemental also you can calculate it back, which is different. So that is how the databases that are being targeted to provide you your size-wise liberation information for a given samples. And so how it works, basically you need to do a sample preparation very similar to SCM, but in SCM it's a surface polishing that you try to do it. But in case of your mineral that you wanted three-dimensional, so then it should actually have your resin which is being coated with respect to certain microscopic analysis targeted multiple surfaces. And you go with the SCM and a combination of EDS, which takes about capturing detailed images and elemental composition. So I'm not going to the complete details, but otherwise you can find out various data sheets that are available from each device. Otherwise, finally, what is important is the data analysis, specialized softwares that actually you can utilize it to identify mineral phases, grain sizes, and liberation degrees that are possible with it. So this is the overall methodology chart that you can able to go with the sequence. So sample preparation to SCM projection, followed by again the data that you can able to go analyzing that. So this is where the backscattering electronic images are being used, which are done through X-ray diffraction, and then we get these the grid-wise mapping, where in each grid how the composition is varying, that you can able to do it. So the grid point energy display to X-ray, they call it as EDS, is being used heavily for determining chemistry and mineral phases to link up. Then once you know the chemistry and then its mineral phases, then you map it with respect to quantitative assessment of how much it is there, and then you go on placing that information. For example, this rock, whatever it is there, they identified that you have about following monazite, magnetite, hematite, pyrite, and chlorite minerals. and you can use them for assessing the grain size distribution, average particle size, as well as the chemical composition of each grid, how they come around it. Then in that process, I think fundamentally we just need to see that this is just we believe that the software is doing, but I think as engineers we should also understand how actually it does. So basically, it's nothing but imaging of these back scattered electronic images, where you see now each phase will have a different intensity that is being reflecting, and you can try and identify these the intensities in a way. You first deagglomerate in a way how you eliminate the background noise and background data, then you focus on these elements, and within the element again you map the grid based identification of the individual point zones, and from the individual point zones you can able to identify your the chemical nature of this solid as well as the mineral nature that is associated. And that is how, for example, from this gray level you go with the segmented particle imaging representing three nature of the mineral, and what are those that you can able to do utilizing. There is again a further mapping of the database. That's what it is coming from. The average atomic number, that means each mineral will have its AAN. So the average atomic number associated with that mineral, and if we can map it, and there is a possibility that the peaks can have a same, so two different minerals can have a same ANN. In that case, you need to go into chemical nature of the elements further refining at the grid level. So that is how you go on identify the mineral phases first based on ANN, and then going into individual the grid range information to differentiate it with if they have the same ANN, what kind of a chemical nature that they have it. And once you identify the chemical nature, now you can rebuild even if they have the same ANN, and then chemical nature can clearly differentiate it what is the mineral composition is going to be. So, and that way now here we see the pyrite and chalcopyrite, and also you have the minerals that are there in the three forms that you can able to see with respect to given rock. So these are back-end calculations and imaging reconstruction would happen from the software point of view for a given instrument, but otherwise we should realize that where we are projecting and what is the data that we are trying to get out. So this is one of the application that you can able to see. So Kiriburu iron ore slimes, because slimes are now today is a lot of, one is environmental concern, second is you also have a lot of valuable iron with it. Can we recycle back your iron? And these iron ore slimes have about 45 to 52% of 53% of iron in it. And guess China, the way they operate iron ore, 35% on average, and they are still the leaders on the iron making with the 35% average iron content. And what we have thrown as a waste is about 45 to 53%. Quite significant, and some of them are even up to 56%. But then the nature of this material is very fine in terms of sizes, and today minus 75 micron is being discarded as a waste. I think some plants they established for iron ore slimes beneficiation plant, but again off late they realized, but these resources are plenty if you go and check most of the iron ore plants. So then one idea came around it, why don't we adopt the mineralogy to understand how the valuable hematite and magnetite are being associated with the other silicate and aluminum material. So this is for them, and we can see as you go by size wise, starting from coarse size about 300 micron to almost all, we talk about up to 1 to 2 microns range of elements are being attempted, and that's the beauty of mineralogy it gives you. But the next question is, how do we use them for designing your beneficiation plant? And that's the next question we should look at it. But I have one small example to illustrate that part very soon. So, and other part is even APMA also gives you quantified information with respect to size wise and composition wise. You can see now that is also indicating that as you go with the different sizes, I mean, these are different samples that are being targeted with respect to hematite ore, geotite ore, as well as limonite and other phases. Where if you see iron, some of them hematite, geotite, they are talking about iron oxide is in the range of, this is like a quantity, it's not a percentage of the iron oxide we are talking about. Iron oxide is this much, but otherwise iron content is going to be about not more than 65% maximum. But EPMA doesn't tell you how it is distributed. It only gives you the sample wise and size wise. Now what we wanted is further going on to utilizing this liberation analysis for beneficiation route, and that is where the target that we wanted. So this data is generated from one of my research way back 2013 to 16. Then what we have taken is one of the iron ore slime sample collected from one of the corporate producers, and we looked at the size wise how the material is being associated. If you look at it, nearly about 75% is below 10 micron. So that's a level of fine material associated. Now, if we today ask what is this P 10 micron, if we look at the pollution measurements, there's a PM particulate matter 2.5, particulate matter 10. Now that means if the slime is being dried and put up in an environment, 75% of the material just goes on an air fly. So that means such a fine material is difficult to process. So that's why industry traditionally they kept this material as a waste and then deposited as a tailings dam. Now from that, I think if you try and look at it, these are the various mineral compositions that you can able to see. And again, they are varying starting from hematite, which is high grade, but otherwise geothite is the one which is associated with a lot of them. So geothite has about 75% mass, which is now you can see those are your iron also associated with the minus 10 micron particle. Now, if you further go into, this is from one of my colleague from Tata earlier when I was in Tata. So he worked on this QuemScam to look at the iron ore slimes mineralogy data. So we can clearly see that coarser particles are rich in hematite, okay, and maybe in terms of some of them are also there with the gibbsite. But as we go with the finer, we are not able to see clearly that the clear demarcation between these minerals is not possible. Looks like all of them are associated with the finer sizes. So then indirectly it says that your iron contents are being locked with the aluminum silicates when you go with the finer sizes. Whereas in the coarser sizes, there is a sufficient liberation that is possible. But when you go with the finer sizes, it's very difficult to liberate your iron despite whatever you do the grinding. Okay, so now knowing this, again further other spot analysis also being attempted, and we can clearly see that your green color, which is hematite, and also the other minerals that are completely associated with the coarser particle, but finer particles, they are still interlocked with the other minerals. Now, when I look at it, the distribution wise, from size wise, iron content, alumina, and total weight fraction, you can see, as I mentioned, that minus 25 to 10 micron, nearly about 78% is being distributed. And then there is alumina. If you try and look at it, your iron is also distributed everywhere. So it's impossible to see that there is any segregation that is possible with the size wise for iron. But there is a possibility for alumina to look at the size wise. That means your iron is too high in terms of the fraction wise, alumina in terms of the finer sizes. Nearly about 75% of the alumina locked with the minus 25 10 micron. Then the one concept that we realized that if we try and separate the minus 25 micron, then up to that you have a limited alumina, but total mass fraction wise is very limited, right? If you can look at it here. Your alumina weight fraction wise, if you look at it, including iron, alumina, they are mainly here. But otherwise in these processes, you have a sufficient high grade the iron content that is possible for you to get into your beneficiation. So then that is what we decided, saying that if you try and beneficiate with respect to the classification near about 25 to 10 micron, there is a possibility that you can able to get the separation of high alumina away, and then you will have it. So that is what we tried, and this is again another medium alumina grade. Here also you can see now nearly about all that material that you can able to do, Al2O3 minus 25 to 30% that you can able to 25 to 10 micron size range you can able to eliminate, and we have processed through some of these the gravity separations and also classification through novel hydrocyclone design to come up as a proposal for getting alumina minus below 2.5%. That means it's a direct pellet grade product that you can able to generate in a single step of a beneficiation route. So I think that's the first component that I wanted to give as an overview of what is this mineralogy, how it would help for our beneficiation of critical minerals. And right now I have illustrated the example of mineralogy with the aluminum iron ore slimes, because they are again a very fine material, very similar to nature of other critical minerals that we target at the smaller sizes. So then if we look at the remaining physical beneficiation methods, let's say today we talk about the lithium. Lithium could be, it is coming from the barren salts, or you can have a spodumene lepidolite that are available in the solid form. But the moment you get a solid form, then I think your conventional run-of-mine mineral processing methods you have to still go through. But then if you are targeting about the critical minerals, the current mineral processing practices, are they sufficient? So for example, we got a material from one of the lead zinc tailing site, and then the industry and through Ministry of Mines, we got that project. And then the idea was if the tailings of a lead zinc are available, can we extract, because lead again there is about a 0.8%, zinc is about 1.5%, and you have a silver somewhere about a 300 to 200 ppm range. So then the project was to see, can we extract these further, because mineral resource of them in India is also again getting depleted. Now we looked at, and then yes, we can try and see what is the best possibility. So one way is we put up this material. These are tailings, and if you look at the size wise, minus 200 micron roughly, minus 200 and 220, and everything is very fine, similar to iron ore slimes. And we put up through the grinding, conventional ball milling laboratory, and we did grinding starting from 20 minutes to nearly about 90 minutes. And we saw that in conventional ball mill, obviously, you cannot go below certain size. Whatever, how much time, doesn't matter, you grind it. After 40 minutes or 45 minutes, we didn't see any difference with respect to final P80 product size. They are stuck at 45 micron or 45 to 50 micron. But our target is, when I looked at the mineralogical information, most of the scope that you can able to unlock them at a 20, 25, 30 micron range. But the ball mill is unable to do anything. Rather, if we try and subject for longer grinding times, what happens? The generated heat makes the particle to agglomerate more and more. In fact, this we observed in the UG lab, where the students, they come and we give a certain nature of the, let's say, lead concentrate. And students, they come and say, sir, after my secondary grinding, I am seeing my particle size is increased. Of course, it would do if the heat is being sufficient enough for forming agglomerates. That is possibly happening. So here, the conventional grinding methods are unable to go and tackle grinding at a smaller size, impossible. Now, that is where the ultrafine grinders are needed for particularly targeting about critical mineral liberation. So here, what are those? What is the need for it, for critical minerals at least? So ultrafine grinding is often needed for the liberation of critical minerals, because these minerals are frequently locked within the fine-grained gangue matrix or occur as elementary small inclusions that can not be effectively separated by coarser sizes. Here it is why. One is fine intergrowth of the mineral phases, particularly if you look at the rare earths, right? And cobalt, vanadium, lithium often occurs micro and nano size inclusions inside a mineral. They are part of silicates, aluminum silicates or iron oxide locked at the nano range. Now, when you subject for conventional grinding, nothing would come out. So that is one purpose why ultrafine grinding needed. Conventional grinding, roughly, I mean, this is industrial. Laboratory is about 40-45 micron, but industrial mills are quite big. The larger the diameter, your grinding size also goes higher range. So this is where they leave 100 to 150 microns and still physically locked, reducing recovery. Ultrafine grinding is needed below 20 microns, sometimes even 10 micron, breaks these associations. So this is where the need for ultrafine grinding needed for critical minerals. Third is, because after liberation, let's say somehow we managed to grind about 10 micron and we unlock the colloidal range of the minerals that are there in the solid form. But after that, how do we separate? So separation below 38 micron is quite challenging. In fact, that is the reason why the industry, mining industry, they never paid attention towards the processing minus 38 micron straight away, because energy point of view, it's so much costly, and there is no effective separation that you can able to enhance easily. Then when you go for that level of informations, so basically we need to look at it. If we talk about critical minerals, how do we actually separate them after liberation? Now, you need to separate for chemical leaching or solvent extraction. Now, all of them works based on surface area. The larger the surface area, the better the efficiency that you get it further down the line. So that is where we need it, increased surface exposure for effective separation. So finer grinding increases the surface area of these target minerals, improving contact with the reagents and leach solutions. So that's a definite advantage we get it. And it's not necessarily that every metal we process through. But I think I do hear many claims from metallurgists saying that we produce nanomaterial by ball milling. I said, are you sure you are doing ball milling or planetary ball mill? No, we do planetary ball mill. Then I asked, can you able to adopt this for tons of the material to do in the daily way? I said, no. Obviously, scale up for planetary ball mills for such large quantities is not possible. So then what we need to look at it from minerals point of view, saying that can we think about the available advanced technology of the grinding that are straight away scalable? And that is what I am focusing here. So now third requirement is overcoming the textural complexity. So this is where many critical minerals have a complex structures, joint grains and exclusion lamina and also interstitial growth. So obviously ultrafine grinding disrupts these structures so that the large phase of valuable mineral can be liberated from the discrete particles. Then further is enabling the advanced separation methods. That's what high intensity magnetic separation, because if you look at the rare earths, majority of them are having a magnetic susceptibility. If you want to separate it, you can do. But then how to enhance the separation process? This is where the grinding can able to give a better surface exposure for magnetic separation, and so as high intensity magnetic separation, selective leaching and fourth flotation all depends on mineral liberation. Without ultrafine grinding, these processes are so poorly yields. And economic necessary for low-grade ores, we are talking about coal fly ash, mine tailings, or laterite, even today lithium. All of them need certain tiny amounts valuable minerals to be liberated and from the large chunks of it. So obviously, the maximum liberation through this ultrafine grinding is essential to make an extraction economically viable. So that is where we need to, I think I need about another 10 minutes maximum, where most of these ultrafine grinders, we talk about it, but I think focusing on product of 1 to 20 micron. And this is the range is very sensible for critical minerals, especially when you are coming from primary, secondary sources. And these ultrafine grinding of a dry powder is also possible, but I think I'm excluding that part because you need to do with the specific mills and other things, and not for the for the purpose of the critical minerals, which most of them we find the critical minerals of such fine material in the wet form, or if not in the slurry form. So then ultrafine wet grinding is done with respect to these the agitator mills, ISA mills and stirred mill. So the ISA mill, I think I will tell about the story later. I think I have the slides down the line. But now these four. And apart from that, I think HPGR is another technology. I think except in India, rest of the world is well adopted. This is coming in the intermediate range. For example, if you look at the secondary crushing and tertiary crushing and grinding, primary, secondary, all of them together you can combine with the one single unit operation with the called HPGR. So the HPGR is a high pressure grinding roll, but energy point of view, specific energy that is being adopted compared to the conventional crushing and grinding, it's actually very high. So you can get a better efficiency with the HPGR, and I will show you the slide on that later at the end of this PPT. So the agitator mills, they are there. They actually produce almost all. The throughput is limited, of course, 4 liters to 1200 liters capacity filled with the liquid, and then you have a grinding media inside. So basically these are rotating at high speed, having the grinding media, and there is a shear action followed by the attrition that happens with the fine particle, so that you can able to get your product close to about a 1 micron or even finer. So that's the beauty with the agitator mills. Again, they are there with the specific applications. Right now they are adopting for certain elements particularly, but I think this is a scope that is possible for our critical minerals. When you talk about our liberation at the micron range or tens of micron range, you can still adopt it. And then the vertical mill, I think these are again there where they produce higher forces than the gravitational tumbling mill, and media is minus 5 millimeter, and you can go on product less than 5 micron. Okay, and of course application that you have to think about carefully, but many installations are there with respect to different minerals, especially when you have a liberation that has been targeted about 10 microns or below 5 micron. Then the vertical stirred mill, these are again another version where, so there is a difference between them. Like here, your the rotation or the vertical mill is actually just curved rotations that are being taken place, whereas in this case it's actually high speed where you have a disc kind of pins that are there. So, and you can actually use this horizontal or vertical, and horizontal one we refer them as the iso mill that we can talk about it. So I think that is a slide that I have it here. So the iso mill was a first in kind for the major mining applications, so mineral applications came. So name itself came from Mount Isa in Australia. So the Mount Isa operates to produce complex copper, lead and zinc, and they realized that a lot of value was getting as a tailings having about a minus 45 micron or minus 53 micron. And I think one of the operator, the plant manager, he realized that why don't we grind below 20 micron? That was the idea. I think the project started almost 30 years back, and today we see this scale up units are established around the world. And that's and then it is actually very similar to what we have seen in the previous slide, that you have again a disc that are there in the horizontal form. And in fact, we do have an iso mill at Hyderabad. I think probably one of our tutorial session will show that instrument that is there. It is not completely installed, but otherwise inside you can see these are being high resistance. The disc are there, but perforations also there, so that slurry can actually move. You will have a high the sharing action happens, but also transportation recirculation makes them so effective for better grinding. And we talk about these technologies, ability to produce very efficient for up to 10 micron. And it is a combination of smart component design and careful selection of rubber and polyurethane components to give a long wear lives with a relatively cheaper material. And iso mill horizontal high speeds can go up to 350 kilowatts per meter cube of a slurry. In comparison to power intensity of ball mill, 20 kilowatt per meter cube, the high power intensity enables iso mill to produce fine particles of high throughput and that are essential for economics of the mineral industry. The largest iso mill now, I think they have gone to 4 meter cube, and widely adopted lead, zinc concentrated, and UG2 and copper. And I think they are not single units. I think you can go for multiple units. And these are adopted for lead, zinc concentrates. And then the HPGR. HPGR, now we know the roll crusher, and then now if we try and adopt them with the under the high pressure regime, we can able to send the particle in a bed of a particle to break it. So then essentially per specific power that we talk about, the power consumption per unit mass is going to be much better utilized here compared to other devices. So these are the various parameters that you can go about it, including packing of this material that you make as a bed of a particle subjecting for your grinding. And they are greatly affect the way the energy is transmitted between the particle and produce totally different kind of product that we get it. So you can see now this is under the pressure. When you are sending you can able to get it. You can replace the tertiary crushing completely with the HPGR and eliminate the grinding that is needed. And you can use much higher fines production and one fixed roll is there, others can be rotated, and also we have a fixed pressure but not the gap. I think pressure is the main component when you try and utilize it for the energy that is there. And this is what we can see. The bed of feed, we are not sending a loose particle. You need to send the certain packing bed so that you can actually impart. So what happens is when they are coming to the contact of the rolls, the pressure that is being compressed on the wall of the particle bed, now the bed particle are also in contact each other. They get a better particle breakage compared to conventional single particle breakage that we see. And then they are again, the scale up is pretty possible. And then there are number of OMAs which can able to make this, and the multiple of them assemblies that you can able to do scale up that are there. Yeah. And breakage intention is most efficient. Breakage compression share is less efficient, that we know. Breakage in the conventional crushers, ball mills is mostly tension, and breakage in the HPGR mostly shear and compression that we go on it. So that's the advantage we go. Whereas this is for a single particle breakage, and in HPGR, not only on the applied surfaces, but also interparticle breakage is being adopted. Okay. Yeah. I think what is the best, I think we can able to see here. So breakage efficiency is better, and again doing at high rates also we get it compared to crusher and mills. So yeah, and I think in all of this, your equipment operation selection should be carefully done. It depends on the feed stock and your feed sizes. For critical minerals, anyway we target to go with the smaller sizes, and ultrafine grinders are definitely needed. The recirculation is important, classifying material and back into that. And the energy consumption, of course, we go with the same route, where if the finer size needed, you need higher energy. But I think ion energy efficiency you can able to increase if you have particles in the bed form to break it. So I think 95% of the energy anyway is not being utilized for breakage of the particles, rather moving the machines and other auxiliary conditions that we use. Otherwise, 5% of the energy is being only used for particle breakage. So for that matter, I think a lot of research going on, and these are the other advances that we can able to see. Because today we are trying to find new resources or for the critical minerals. And then their geometallurgical characterization is unknown for us. You have to do for every new material that we go for searching. So faster breakage characterization devices needed. I think a lot of innovations are happening. If you can search all of them. New grinding media. So, for example, this is relay grinding, RGM. They say that in a conventional ball milling, if they use specific regrinding media, so I think they try to prepare high strength, the artificially prepared grinding media, but it has a non-spherical shape. And they claim that having a non-spherical shape would trigger a better contact with the finer particles to be broken. So I think it's a claim, but I think somebody is from Belgium, they are claiming it, saying that we don't have to reinvent the new grinding machines, but reinvent or invent the new grinding media that makes more efficient. And also the electrofragmentation. I think this is a new approach, probably you can do it, or microwave treatment for some of the particles. Indirectly, what you do is the electrofragmentation or a microwave treatment side, you are actually inducing micro cracks within the particles. So that conventional grinding cannot be replaced, but I think assisted with the preconditioning can able to do better grinding and separation of the broken, valuable and unvaluable materials. So these are few of them, but as well as plenty of them you can find in the latest editions of the communication conferences. In fact, communication conference goes every 2 years. That is happening in South Africa, Cape Town. And even there is another congress, we call it as SAG conference, which happens in Vancouver, Canada, every 4 years once. It's like a World Cup marathon for us. Even to get your paper accepted for oral presentation in a SAG conference, that means you are recognized one of the world expert in that field of communication. So we got that in 2016, and then after that, last year we supposed to do, but I think Aman graduated quickly and hurriedly for his job. So I think there are implications for. So in mineral processing, I think every sub-theme Classification is also another conference that happens. Even tailings management, bulk solids, and then critical minerals. I think every 6 months I am seeing at least one international conference is happening. So I think now world is moving fast. Everybody is trying to knock the door and kickstart the early, findings and research activities. So I think we are also in that race at Hyderabad. Probably in December we are conducting ATM, 2 days conference, which is combined with the Indian Institute of Metals NMD conference. But I think this time Minister of Mines came forward, say that let us extend 2 days of conference focusing on critical minerals and advanced materials. So December 3rd and 3rd to 6th is a major conference, but international conference 3rd and 4th, 2 days that we are running. So we are also now inviting experts worldwide, including India, on critical minerals who can deliver excellent talks based on their contribution. So I guess with that, I think I can conclude my first talk on advances on critical mineral processing related to mineralogy and comminution. Yes, please. Yes.
So what does it mean?
So basically for a given input energy, whether your required product size production rate is higher or less. So basically we talk about how much energy you need to consume for getting your product. So that way, when you look at the typical crushers, either one surface or two surfaces are involved and you're importing the compression forces to break. And it's not at the edges of the particle, but it's a catastrophic breakage happens. But at a time, only one particle, right? I mean, basically that the mechanism. When you go with the bed of particle in a packed condition, when you apply the compression forces on the two surfaces on the sides, but as the particles are in contact, they actually induce this stress transmission and then they break themselves quickly. Then your effective energy that is needed to break is much less compared to the conventional two surface breakages.
Then others were mentioned as good, but then why it's HPG and
high pressure, because they are applying not just about only the rolling action, but also how to maintain the solid particle in a bed composition. So when you apply the pressure, the particle doesn't disintegrate themselves when they are passing through. So you apply a high pressure in the entire enclosure. And then the pressure comes two ways. One is through rollers also comes, and overall container also you keep it. So it's like you involve the movement of the rollers at high pressure, and the chamber also you keep it high. Yeah.
in terms of using less energy.
Yeah. So they use less energy for producing the same product of conventional. Yes.
So whatever you're mentioning is with the ultrafine grinders in the range of micrometers, less than 10. And when it comes, and these resources from the primary and secondary resources, as you mentioned.
Yes.
But what about the rare earth materials and critical minerals which are existing in very ppm forms and very less concentration?
So that's what I think in the beginning, the need for critical minerals, ultrafine grinding is, they are actually locked in the aluminum silicates and silicate structure in the micron range or nano range. Unless you break the particle to at least a micron range or closer to colloidal range, you may not be able to have any advantage of surface exposure. See, for example, you want to separate these using flotation because they have the certain hydrophobic nature. But to get the surface exposure to that level, you need to have some liberation. Otherwise, what happens? The particle, if I have a silicate material, if the particle mass is interlocked, I'm not going to activate my flotation process for those valuable material. So that is the reason why ultrafine grinders are going to play major role and compared to other conventional grinding techniques.
These are mostly wet methods, right? Not dry methods.
These are mostly wet. Dry are also there, but I think the issue with the dry is and others are there. But so probably there are a couple of varieties of them available. So basically, you can integrate, for example, coal, right? Fine coal. You can also do classification plus grinding simultaneously. And if you try and look at it, you can able to generate the particles of close to about or less than a millimeter, even using air classifier come the coal breakage.
Are there also options for recycling? water waste, or is there another process?
Recycling also, some of them you can apply, but only thing is you have to eliminate your heat materials, for example plastic. But the moment you use them plastic material in these devices, basically you are not able to take any advantage. So basically segregation of these non-rigid particles should be done prior to that. So that's why the acid dipping followed by the dielectric properties based, if you can segregate it, then further refined black mass that comes, for example, the recycling side, you can able to directly use it. So the pre-treatment is needed for any machine that you adopt for. So straight away you cannot use it here. Yeah.
It's an nanometer process. So to want to extract also, because there is actually a mine, big mine, I think it's the world's largest mine near Tirupati.
Okay.
Ferrites.
Okay.
Ferrites.
Right,
So
right.
there is lots of staff might be there, but some evidence also there is this fluoride present in that
Okay.
through GSS or whatever.
Right, right.
So how can we extract with the help of these?
But so what is the nature of those metal? I mean, are they basically elastic or like, no, the characteristics of the solid particle that you have to see. So anyway, you have to go through the conventional runoff mine comminution process. But these are ultrafine grinders are only meant for once you prepare so your feed for these devices is supposed to be a ball mill product. I mean, that's a simple understanding way. So you have to apply those anyway, but you may not be able to go down below 50 micron to produce further fines. So then this is the technology that you can apply it. So you have to see feasibility wise at what size your particles of a valuable mineral are getting liberated. So that feasibility analysis has to be done using your, the route of a geometallurgical route, where you get a borewell samples, test it, and then reduce the size equally and find out what is this, the mineralogical characterization, and then come up. So that's a process. Traditionally, it is advanced. They take it. For example, if Australia, they are attempting any mine leasing. Before that, the geometallurgical characterization already done by a number of agencies. So that is a process that we need to enable in India, which is not currently being well practiced.
Yes.
Yeah. So I think it should be done with the conventional followed by, based on what is the liberation size that is expected to have your mineral to be enriched, that size we have to identify. We have certain extent, I mean, now we have also isomill. So you come and see whether there is a scope for us to do it. But mineralogical point of view, we are procuring the MLA. So mineral liberation analyzer, the discussion is going on with the vendors. And Coal India sponsored a major project, 100 crores already to us. And part of it, we are procuring it. And it should be ready within 6 months' time with us. And we can take up the geometallurgical testing of the samples that are needed for any industry. Right now, we can extend up to SCM EDOX level or EDS level, but then the database are limited. Whether your mineral required mineralogical database is inbuilt or not, I had to check. Right. Okay. All right.